So I briefly mentioned it in the previous videos, but I said that we wanted our Turing machines, instead of just being able to accept and reject strings, we wanted them to also be able to compute some functions. And so that's why we had a set of halting states instead of a set of accepting states. So this video is going to go through an example of a Turing machine which computes something. What I need you to remember is just what the definition of a Turing machine is. So as I said before, instead of accepting or rejecting a language, the Turing machine that I'm about to show you is going to compute a function. Specifically, it's going to take a string in a certain alphabet and it's going to output a different string. And that string is going to depend on the string that it was given. In this case, it's going to be a very, very simple function because I don't want to take you through a really complicated definition of a Turing machine for your first go. So it is not going to do something that is fundamentally harder than we could have done with, say, a finite state machine with a slight modification. So this isn't showing the true power of the Turing machines at the moment, but I just wanted to take you through an example of defining one. So I glossed over it before, but what our Turing machine is going to do is take a string of A's of a certain length and output a string of B's of the same length. Nothing terribly complicated. But we do have to define what we mean when we say the machine is given an input and produces an output when we're talking about an infinite tape, because really there's no idea where on that tape something is. So for this course, our assumption will be that when a machine starts, it starts on a blank and whatever is to the right of it is its input. So if we want our machine to deal with this string of 4 A's, then we put it there and the machine starts with the tape head to the first blank to the left of that. And we are going to also assume that when we finish, we are going to leave the machine in the condition that whatever we want to be its output is to the right of it. So the machine is going to stop on a blank, so that's going to be our convention, and then whatever is to the right of that blank is the output. So if we want to output a string of 4 B's, we need to stop on a blank, and we need to have 4 B's coming immediately after that. So what our machine is going to do is it's going to go through, and every time it sees an A, it's going to wipe that A out and replace it with a B. And then as soon as it sees a blank, it's going to know that it's finished with the A's, and it's going to move the tape head back to the left so that it can halt and output a string of 4 B's. So the state machine for this one is fairly simple. The state comes in, and remember that the transition that is defined is based on what is currently under the tape head, and our assumption was that what's currently under the tape head is a blank. So upon seeing a blank, our machine is going to bounce over here and not write anything over the top, so it's going to leave the blank there, and it's going to move the tape head to the right. So now we're in another state. At this point, our machine, if it sees an A, is going to write a B instead, and then move the tape head to the right. So because it does that and loops on the state, every time it sees an A, it's going to change it to a B, and then move over to the next spot. So it's going to keep doing this like this. And eventually, the tape head is going to be sitting here pointing at a blank. So we need a transition from the state that we're currently in that operates on a blank. So upon seeing a blank, our machine is going to leave it blank and move to the left. Now while it is here, while ever it sees a B, it's going to leave the B there and it's going to move to the left. This will mean that our machine will continually loop on this new transition that we've had and bounce to the left until it gets to here, at which point it's going to see a blank. So we need a definition for what to do with a blank. Now what we want to happen at this point is we want our machine to just stop. So upon seeing a blank, we're going to leave the blank there, and we're only allowed to have our machine move left and right, so our machine is going to move left and then our machine is going to transition on, is going to see a blank, leave it blank, and then move right. At this point it will have moved left once, and now it will move right once. And here we're going to have a state, so if we call these state 1, 2, 3, 4 and 5, we want our machine to halt here, so H will be just the set containing the state 5. So our tuple definition will be K is equal to 1, 2, 3, 4, 5. Our input alphabet is just A, and our tape alphabet always contains blank, and obviously must contain all of the elements from the input alphabet, and in this case it also contains a B. Our start state is equal to 1, and our transition function contains all of these transitions that we've defined over here, as well as probably a few that transition off into maybe a dead state that we might have defined. Now, one of the things you can see from this is that building Turing machines in this tuple way, or as finite state machines, gets very complicated quickly. That was an incredibly simple function, and it got to 5 states and started to look a little bit complex already. So what we're going to actually do when we're tackling real problems with Turing machines is define a special macro language. And this language, which you're going to get shown in lectures, makes it much easier to build up machines. And one of the other things it does is lets us use modularity. So instead of just having this big gargantuan finite state machine, what we're going to have is a description of a few machines in macro language, and then the ability to combine them into more powerful machines later. The other option that we'll do in many cases is just to describe the machine in clear, careful English, because often we can describe them that way and it defines exactly what the finite state machine does. But we do have to be careful that we don't end up describing something overly complicated that maybe the Turing machine can't actually do. So if we describe it step by step in clear, careful English, then we can describe a Turing machine in this way, and it's much less complicated than trying to define it as a 6-tuple. So what you should now know is that we can build Turing machines that compute functions given input strings, and in reality we could do that with push-down automata and finite state machines if we slightly modified the definition, but we didn't bother with that because when we get to this point, this is when we start talking about functions. And you should know how to build at least one Turing machine for a very simple function on strings.